All right, let's get going on today's meeting. So what we're going to be looking at today is we are going to introduce the final test that we are going to be covering in this Introduction to Statistics course, and that is the One-Way ANOVA. So this is going to be the last new test that we take a look at, and we're going to see what situations it applies to, how to run it. But first today, we're just going to introduce the idea of the ANOVA, see why it's needed, see why we need a brand new test for this, and some of the dangers that you can fall into if you do not use the correct test. So we are not going to be doing ANOVAs and SPSS in this meeting, but we are going to finish up our look at chi-squared for association using SPSS today. So we'll wrap that up. And one more time, both of these are in service of our greater goal of becoming able to do inferential statistics so that we can expand the scope of our powers, expand the scope of our influence, expand the number of people that we can help using psychology by being able to intelligently and objectively and without bias move from what we know about a sample to what we can conclude or infer about a population. So on the schedule for today, we are going to do some SPSS for the Do It With Me demos wrap up. We're going to go back to the studies on gender differences and receptivity to sexual offers. Last time we answered the questions, does gender affect accepting an offer, accepting a date? Today we're going to finish off by taking a look at whether or not gender affects accepting an invitation to bed. And then we're going to take a look at how you can interpret whether the results were different in 1978 versus 2025, even if you don't have the skills necessary to actually run that test yourself. So one of the great things about developing your skills in certain tests and knowing how to do certain tests in statistics is that those basic logical approaches will help you interpret tests. Even if you don't know how they're done, you'll still be able to intelligently interpret them. So we're going to take a look at some results from 1978 and 2025 replication that are beyond the scope of this course, but thankfully will not be beyond the scope of your understanding in order to make sense of them. And then we're going to introduce the idea of one-way ANOVAs. We're going to spend some time discussing why do we need this new test, this new way of taking a look at statistical means and inferring about population means. So we'll recap some of the significance tests that we've already done and show you a secret common thread that they all had. And then we're going to talk about the danger of doing multiple tests as a way of explaining why ANOVAs are necessary. And we're going to focus in on a very controversial study from 1969 by Dean and Richardson, which was the analysis of the Minnesota multiphagic personality inventory profiles of 40 college-educated overt male homosexuals. And we'll take a look at the incorrect use of statistics to analyze the results of this research and some of the harmful effects that that had on the treatment of homosexuals in our culture. All right, but first, before we get to ANOVA, have to wrap up our look at chi-square tests for association. So just a really, really quick recap. We've been looking at gender differences and receptivity to sexual offers, both the 1989 publication that reported research from 1978, as well as the 2025 replication of that research. And just to, again, jog your memory, the research was based on Confederates, either female experimenters or male experimenters, and they would approach opposite sex strangers on a university campus. And once they selected the subject and they approached them, they would simply say, I have been noticing you around campus. I find you to be very attractive. And then they would randomly ask them one of three questions, and only one of the three, specifically, would you go out with me tonight? Or would you come over to my apartment tonight? Or would you go to bed with me tonight? And then the dependent measure was what was the answer of the selected subject. And they had females asking male subjects, and then they had male experimenters asking female subjects following the same script. I have been noticing you around campus. I find you to be very attractive. Would you go out with me tonight? Or they would ask, would you come over to my apartment tonight? Or they would ask, would you go to bed with me tonight? And again, what was it that the subject answered? So the study took a look at the differences between the answers from different genders, so how do males answer and how do females answer. And then the 2025 replication can be compared to the 1978 original study, where to see if these types of answers have changed over the 30 plus years since the initial study. So let's take a look at some more data. We'll do a couple of more analyses, and then we'll interpret one of their larger findings. So we're going to now focus on the would you go to bed with me tonight question. So we're going to take a look at whether or not the sex of the subject is associated with the answer to the question, would you go to bed with me tonight? So do the answers of females differ from the answers of males? And the null hypothesis for this is that there is no association between subject sex and the likelihood of saying yes, that the pattern of yeses and nos is the same for males as it is for females. That's what an association would mean. And then the alternative hypothesis, or the research hypothesis, is that there is an association between subject sex and the likelihood of saying yes. And one of the reasons this is written out in just plain English language is because mathematically, as we're going to see soon, it would be very difficult to write out all of the possible associations. So we let the English language do what it's good at, just generally summarizing. Alternative hypothesis, there is an association between subject sex and likelihood of saying yes. And just to kind of put a visual to what the data was, here we have a bar graph of the data. On the x-axis, we have the answer that the subject gave, either yes or no. On the y-axis, we have the frequency with which those answers were given. 16 males were approached, 16 females were approached, and the blue bars are the male responses, the pink bars are the female responses. And you can see that seems to be a very different pattern. And the alternative hypothesis says that there is an association between subject sex and the likelihood of saying yes. What that means is that the pattern of responding across gender for the yes answer is not the same as the pattern of responding across gender for the no answer. So the alternative hypothesis is saying that those two different patterns there that we see, those are actually statistically significant. They're real patterns, they're stable, and we can run this experiment over and over and over again, and we'll still find this pattern. On the other hand, the null hypothesis says that there's no association between subject sex and the likelihood of saying yes. And what that is saying is that the pattern of yes responses are the same as the pattern of no responses, and any visual difference that we might see there is just chance. And if we ran this experiment again, we would get a different pattern. And if we ran it again, we would get a different pattern. And it might visually look different to us, but it's just a chance occurrence that the bars fell out the way that they did. And there's no real difference between the way that males and females answer the question of, would you go to bed with me tonight? So what we're going to do now is we're going to test between those two hypotheses. So for this, we are going to be using SPSS. So if you haven't already, make sure that you have SPSS open before you proceed. And then also we are going to use the chi-square association SPSS demo. So if you haven't already, open that. If you're watching this on the video, link is in the description. And we're going to start off with the 1978 data here. And once again, we have the question, would you go to bed with me tonight? We have the sex of the subject and the answer that they gave. And every single row here is a different subject. So this is a female that said no. This is another female that said no. In fact, in this case, as we can see, all 16 females said no. And then we have the males that said yes. And we have the males that said no. And those are all the responses. And then you can see the numbers here in the Excel sheet as well, just to give you the kind of breakdown of what's going on. So we're going to zoom through this a little bit quicker than we normally would, because this was a take-home challenge from the last time that we met. So what we're going to do is we'll just go through the steps. and hopefully you were already able to successfully complete these. If not, here's how you do it. So we're going to highlight and select all of the subject raw scores. And again, make sure that you only select the scores. Do not select the headings, just select the scores or the responses. And we are going to copy that. And we're going to go over here to SPSS. And in row 1, column 1, we are going to kind of do that same thing again. We're going to try to paste. And it's going to give me the V. And I'm going to delete that. And now in row 1, column 1, we can paste. We can paste. So we've pasted in our data. SPSS has named the variables the horrible way that it likes to name variables, var 00001 and 00002. So we're going to go down to variable view, and we're going to change those to things that a human mind can make sense of. So we're going to change that first variable to sex. We're going to change that second variable to answer. We go back to data view. We see that the variables are now named correctly. And then we're going to go up here to analyze. We are going to go to descriptive statistics. So not where we usually went, compare means or proportions or non-parametric tests. So remember, for the chi-squared test for association, we go to descriptive statistics, we go to crosstabs. We're going to put sex as the rows, and we're going to click on answer and use the arrows to put that into columns. Statistically, it doesn't matter which one is rows and which ones is columns, but that is the convention to use the explanatory variable in rows. And then up here in statistics, this is where we're going to choose chi-square. And we're also going to choose phi and Kramer's V so that SPSS will calculate effect sizes as well. Do not choose anything else, otherwise you'll have an 800-page output. And then we hit continue. And then in terms of cells, by default, it has observed cells clicked. We could click on expected. We could click on percentages for rows and columns if we wanted to, but we don't need to do that for this question here. So we're just going to continue on that. And we hit OK. And we get our output. And now we are ready to take a look at what SPSS has calculated. All right. So here's the numbers that we got. Let's zoom in on those a little bit and see what they actually mean. So that top table, first off, we don't need that. We're not missing any cases. So we don't need to analyze or do anything with the case processing summary. The first one we want is this cross tabulation, sex times answer cross tabulation. And we want to make sure that we double check it so that our counts are correct. That gives us confidence that we entered in our data correctly. So we take a look at the variable sex and we see that we have the right number of females and we have the right number of males and the right number of females saying yes and no, right number of males saying yes or no. And then we double check the variable for answer and we see that we have the right number of yeses and we have the right number of nos. And this is just something that makes sure that we're not making any mistakes, that we have the beginnings done correctly so that we can do interpretation with confidence. All right, next we go down to the chi-squared test table, and the row that we're looking for is this Pearson chi-squared row right here. That value right there, 19.2, that is your chi-squared statistic. And with 1 degree of freedom, that chi-squared statistic occurs less than 0.001 probability. So that is your p-value, that asymptotic significance two-sided. That is the p-value that you're looking for. And then down here on our symmetric measures table, we have our effect size. And in this case, we're going to focus in on Kramer's V. And we can notice that in 1972, there was a significant difference between the way that males and females answered this question. And the effect size, as measured by Kramer's V, is 0.775. And the maximum effect size on Kramer's V is 1. It goes from 0 to 1. So this is a rather large effect size. So not only is the difference significant, but also the size of the difference or the effect of the difference is large. And that's what Kramer's V is analyzing. So remember that Kramer's V of 0.775, that is the large Kramer's V. But importantly for our null hypothesis, the probability of getting a chi-square statistic of 19.2, if the null hypothesis is true, is 0.001. That's the probability of that occurring. So it's a very low probability, much lower than our alpha level of 0.05. So we reject the null hypothesis, we accept the alternative hypothesis, and we conclude that for 1978, there is an association between the sex of the subject and their response to, will you go to bed with me tonight? All right, so that was 1978. What happened in 2025? So this was data from the replication. So would you go to bed with me tonight, asked by a male, or would you go to bed with me tonight, asked by a female experimenter? And once again, the null hypothesis, exactly the same as it was for 1978. Null hypothesis, there is no association between subject sex and the likelihood of saying yes. Alternative hypothesis, there is an association between subject sex and the likelihood of saying yes. There's the data for the 2025 study. And one thing to just kind of notice, if you remember the 1978 study, the amount of no's for the 2025 study is massive. So we'll have a little bit more to say about that in just a moment. But the alternative hypothesis is that there is an association between subject sex and the likelihood of saying yes. That means that the pattern of answers that you see for the people that said yes is different than the pattern for the people that said no. So the number of females and males that said yes, that pattern is different than the number of females and males that said no to would you go to bed with me tonight. So the alternative hypothesis says that those two patterns are different. The null hypothesis says there is no association between subject sex and the likelihood of saying yes. So it is saying that those two patterns are the same. So again, visually they might look very different. But what the null hypothesis is proposing is that that is just chance variation. Those are just noise, random variation. And if we ran this study again, we'd get a different pattern and a different pattern and a different pattern because it's really just no association between the two. They're just random fluctuations. All right, so let's see which of those two is the actual case. So this was our previous analysis, so we can close out of this so that we don't get confused. And then this was our previous data set. And when we used to do t-tests, it was enough to just highlight these two columns and delete those out. But with the chi-square test for association, SPSS does not do well with this maneuver. So the safest thing that you can do is instead of just deleting it and then using this data set, we're going to go here to File, and we're going to go to New, and we're going to open a new data set. So File, New Data, just so that we know that we got it. And then let's just close out of this data set here. Now we know we have a fresh data set. We know that we're not going to get any carryover from previous chi-squared analyses, so we know that we're safe. So now we're going to go to our data. So we go back to our Excel sheet here, the chi-squared association SPSS demo. And we were in the 1978 data. So we're going to go down to our sheets here, and we're going to go to KNG bed. And we click on that sheet. And this is the 2025 data for the answer, would you go to bed with me tonight? And again, it's set up exactly the same. Females that said no, all females said no, males that said yes, males that said no. So we are going to copy that data, go down to SPSS, column 1, row 1, we are going to paste. And then once again, our horribly named variables, automatically named, not very good. Go to variable view down here, change var 0001 to sex, change var 0002 to answer, to answer, can't get it right. One of those days. All right. We change it to answer, and now we do the same analysis. We go to analyze. It's the same situation, so it requires the same analysis. Analyze descriptive statistics. Go down to crosstabs. Move sex into the rows. We move answer into the columns. Remember that SPSS will not remember what you have entered in your chi-squared selections because this is a new data set that we had to open. So once again, we choose chi-square. Once again, we choose phi and Kramer's V to calculate the effect sizes. We hit continue. In terms of cells, only the observed, although if we needed other ones, we could. This is where you would select those. We hit continue, we hit OK, and we have our output here. And our output is, let me just see. Our output is wrong. Did I do this wrong again? This is just one moment. Yeah. All right, let me see if I can figure this out. So this is another moment here. And I'm not entirely sure what's going on. I don't know why SPSS is betraying me like this. But this is yet another moment just to highlight why we check this table right here. So this table right here has saved us once again, because if we look at our data, we're supposed to have 16 females that say no, 0 females that say yes, 11 males that say no, 5 males that say yes. And SPSS is letting us know here that we have 16 females that said no, 0 females that said yes, 4 males that said no, and 12 males that said yes. That's the 1978 data. So somehow SPSS is still remembering that 1978 data. So let's try this one more time. File, new, data. Go back to our Excel sheet here. Highlight, copy, paste, variable view, sex for the first variable, answer for the second, analyze, descriptive statistics, crosstabs, rows is sex, columns is answer, statistics is chi-squared, and phi is Kramer V, cells, just the observed, we hit OK, and now we get the right numbers. So again, I'm going to keep, this is not getting edited out of the video, because just one more time, the importance of checking this table right here has been very, very strongly demonstrated. I don't know why SPSS grabbed the old data, but it did. And if we went forward analyzing that data, we would get a completely wrong picture of what happened in 2025. So once again, we checked this sex times answer cross tabulation table. It saved our skins. So now we have the data that looks correct. So now we can analyze it. So just one more time, because it saved us live here in class multiple times. Check that top table, that sex times answer cross tabulation table. Make sure that you have the right number of females who said yes and females who said no, the right number of males who said yes and males who said no, and then the right number of answers. So the right number of females said yes and males said yes, the right numbers of females said no and males said no, before you proceed with your analysis. And again, this has saved us. I think this is like the third time that this has saved us. So nice to see it in action. Going to have to build up some more trust with SPSS. All right, now we take a look at the chi-square tests. We take a look at this table here. For your chi-squared statistic, it's your Pearson chi-squared. That's the statistic right there, 5.926. That's the degrees of freedom. And that chi-squared statistic, if the null hypothesis was true, that value of 5.926, we would see a value that extreme or more extreme, just 0.015 with a 0.015 probability. So that is just 1.5% of the time. That is an incredibly low probability, which means that it's very unlikely that the null hypothesis is true. So we reject the null hypothesis, we accept the research hypothesis, and we say that yes, sex of the subject is associated with their answer to, will you go to bed with me tonight? But interestingly, if we take a look at the symmetric measures here, while the story of the significant effect is the same as it was in 1978, it is very interesting that if you measure the effect size with Kramer's V, the effect size is much, much smaller. So in 1978, there was a significant association between sex and the answer to, would you go to bed with me? In 2025, there was still a significant association between those two, but the effect size in 1978 was much larger than the effect size in 2025. So while there still is a significant difference, the size of that difference has decreased over time. All right, so the last thing that we're going to take a look at is the null hypothesis and the research hypothesis, the question that we do not have the skills to analyze with what we're going to be able to cover in an introduction to statistics course. So we're not going to be able to run this test, but I just want to show you that now that you know some of the properties and some of the logic behind significance testing, you can basically interpret any significance test in a more intelligent way and know what's going on. So now we're going to take a look at the null hypothesis of the three-way interaction. So the null hypothesis for the three-way interaction is that, or the three-way association, is that there is no association between subject sex, who is getting asked the question type, which one of the three questions are they asked, and the likelihood of saying yes. So now we have three variables that we're looking to test an association between: subject sex, question type, and the likelihood of saying yes. So the null hypothesis is that there's no association. The research hypothesis is that there is an association between subject sex and question type and likelihood of saying yes. And what this basically says, or what this basically is telling you, is that across the three variables, here we have the yes answers at top, the no answers at bottom. So across all these three variables, the patterns are not the same for those patterns of answers. So it's just like what we were discussing with an association between two categorical variables, but now it's just expanded out to three categorical variables. But the idea still remains the same, that the null hypothesis says that even though visually those patterns might look different, those patterns of answers might look different, they're not actually different. They're not truly different. That's just random variation. The alternative hypothesis says, no, those patterns are different. At least one of those patterns is different than some of the other patterns. So what was the answer to that? We don't have the techniques in this course to actually run that analysis. However, using our knowledge of significance testing and hypothesis testing, we can intelligently interpret what the researchers found. So as they report, however, as can be clearly seen in table 1, sex of requester, sex of subject interacted with type of invitation, chi-squared 2 degrees of freedom equals 29.33, probability less than 0.001. So even though we don't know how to run this test, we know what a chi-squared statistic means. It means that this pattern of data led to that chi-squared statistic. So the samples that we have with the pattern of data that they gave us led to a chi-squared statistic of 29.33. And that has 2 degrees of freedom. We might not know exactly why, but we have an idea of what degrees of freedom mean. But importantly, the probability that that chi-squared statistic would occur if those samples were taken from a population where there was no association between sex of subject and type of invitation is that probability right there. So that p-value is 0.001. It is incredibly low. It is much lower than our alpha level of 0.05. So that's why we can interpret this and say, yes, there is an association between the three variables. We can understand the proof, even though we might not be able to calculate those specific numbers. And importantly, notice that in the 1978 data, there was an interaction between all three, or there was an association between all three variables: sex of the subject, type of question, and whether or not they said yes or no. However, when we go to the 2025 study, same null hypothesis, there is no association between subject, sex, and question type and likelihood of saying yes. Same alternative hypothesis, there is an association between subject, sex, and question type and likelihood of saying yes. Much different pattern of results compared to 1978. Much more individuals or subjects saying no to any invitation in general. However, when we take a look at that pattern of responding, and we ask ourselves, is there association? Is there an association? Are there different patterns for the sex of the subject, male versus female, whether they answered yes or no, and what type of question they were asked? Are there different patterns for those? The actual report here says, in contrast, we found no support for hypothesis 2. There was no significant interaction between gender and type of offer. Chi-squared, 2 degrees of freedom, statistic equals 3.53, probability 0.086, with a Kramer's V of 0.19. So once again, we have a chi-squared statistic. We know that that means that that pattern of responding from the sample produced a chi-squared statistic of 3.53. We know that it has 2 degrees of freedom. And importantly, we know that under the null hypothesis, the chances of getting a chi-squared statistic of 3.53 or more extreme is a probability of 0.086, which is approximately 9%. So our probability of getting a chi-squared statistic this extreme is 9%. 9% is greater than our alpha level of 5%. So we cannot reject the null hypothesis. We accept the null hypothesis. We reject the alternative hypothesis. And we conclude that there is no association between gender and type of offer. And then we have our effect size right there. And you can see that even if we did reach significance, that effect size is incredibly, incredibly small. So in the 2025 study, there is no association between subject sex and question type and likelihood of saying yes. We accept the the null hypothesis. In 1978, there is an association between subject sex and question type and the likelihood of saying yes. So there has definitely been a change in those intervening years. So we're going to end our look at this study by just taking a look at some reasons for why there is a change. So just in terms of a summary, is there an association between gender and accepting an offer? 1978, yes, men were more likely to accept offers than women. 2025, still yes, men were more likely to accept offers than women. Is there an association between gender and type of question? In 1978, yes, explicit questions led to a bigger gap between the responses of the two genders. However, in 2025, there was no association. It was basically the same gap for all questions. Men were more likely to accept invitations, but that did not change as the questions changed. So it had the same gap for all questions. And then, did receptivity in general change across time? And the answer to that was yes, receptivity to any question was much higher, much larger effect sizes in the 1978 study and much lower in the 2025 study. So what are some of the possible reasons for these general patterns of results? So one of the possible reasons that has been suggested is just a dramatic normative and cultural change over the past 45 years. So the social world of dating and sexuality has changed substantially since 1978. Approaching strangers with propositions is now perceived as unusual. It used to be perceived as just par for the course. Now it's perceived as unusual, potentially unsafe, and actually socially inappropriate. And one of the researchers that I remember pointing that out is a researcher named Logan Urey, I believe. And she's a behavioral scientist and author of an awesome titled book, How to Not Die Alone. So that's kind of setting the bar, I think, really, really low. But it just kind of shows you the differences between the dating world now and the dating world possibly in 1978. So acceptance for both genders, the rates have collapsed similar to earlier decades. And it has just dramatically decreased over time across both genders. Other possible reasons for the change between 1978 and 2025, it might just be that the original interaction effect was not that robust. It might just be that there was just a chance that those two were replicated in 1978 and 1982, I believe. It might have to do with the fact that only 16 individuals were asked in each of those particular areas. It could be that the interaction was possibly due to things that were culturally bound in the late 70s, early 80s, American college campus experiences, influences by norms that just no longer operate. So it could be that it was a historical effect and not something that is an actual psychological, necessarily innately programmed psychological effect. Other possible reasons, differences in the samples, 1978 and the 2025, could have been very, very different, especially in male sociosexuality. So this was something that we didn't really go into. It was an added thing that the 2025 study measured, but they gave their subjects uh, a test of sociosexuality. And what sociosexuality, it measures a person's willingness to have sex without emotional commitment. So that's what this is a measure of. So lower sociosexuality scores means that you have less openness to casual sex. And what they found was that in 2025, the samples that they had, especially the men, were vastly less promiscuous than they had been in previous decades and in previous studies. So the male participants in the replicated study especially seem to have unusually low sociosexuality scores, there we go, compared to just normative data in other studies. And then finally, there's been a large shift in safety, risk, and social learning perspectives. So the idea that the social and safety perspectives have shifted is massive. So key changes that occurred in the late 70s, early 80s, the sexual revolution was just stabilizing. It wasn't accelerating anymore, but it was stabilizing. So that idea of open casual sex was something that was permeating the culture. But then right in the mid 80s, you had the HIV/AIDS crisis, which is the biggest single shift in people's views on casual sex. In the 90s, you had the rise of internet dating and online dating, which made meeting people in public just seem extremely weird and just extremely unnecessary and just not appropriate. And then things like the Me Too movement, things like the rising safety concerns around casual sex and around ideas of sexual assault, avoidance of strangers, social messaging around stranger danger, and then also just changing gender norms, the decline of traditional masculinity scripts, the idea that, you know, just getting the highest number of sexual interactions that you possibly can is no longer something that gains you status in males. And then this one was interesting. Dating is now often perceived as a risk managed activity. So younger generations, they seem to be more anxious about dating. They're more risk averse than they are adventurous. There's less alcohol consumption. There's fewer sexual partners on average. So it does seem to be less of a perspective of engaging in an adventure and more of a perspective in managing a potential risk. And all of those could potentially explain why we saw that massive change in the patterns of responses for 1978 versus the patterns that we saw in 2025. All right, so that is going to be our wrap up of chi-squared tests for association. Any questions on that, comments on that before we move on? All right. So now we're going to introduce the idea of the one-way ANOVA, and we're going to see why this is such an important test, such a very useful test, but very, very necessary. This is an absolutely necessary expansion of the t-test that will allow us to answer psychological questions that are extremely interesting that cannot be handled well using the t-test. So before we get into that, we are just going to have a brief all right, nothing's working today. We're just going to have a brief moment where the clock that I specifically took time to animate going backwards is not going backwards. But anyways, I'm not bitter. Previously on significance testing, you might recall that we took a look at certain previous studies, such as Daryl J. Bem's Feeling the Future, Experimental Evidence for Anomalous Retroactive Influences on Cognition and Effect, which I still really wish was titled I Knew This Would Happen, Experimental Evidence for ESP on Cognition and Effect. And if you remember that study, it asked whether or not subjects could correctly predict which side of the computer screen a picture was going to appear on, specifically an erotic picture, before the picture actually appeared, before the computer actually decided which side it was going to show that on. And if you recall, the subjects predicted correctly 53.1% of the time. And the null hypothesis for that was that the percentage of predictions for the erotic pictures would equal the percentage that would be expected just by chance, and that would be that it equals 50%. Importantly here, I want you to notice that there's only two categories here. There is the erotic pictures, and we're comparing it to chance. So that was something that could be used with a t-test. When we took a look at some evidence for heightened sexual attraction under conditions of high anxiety, this was the bridge experiment, where subjects either crossed an experimental bridge or they crossed a control bridge, and then they were asked to give a story about an ambiguous subject, and they were measured for how much sexual imagery was in that story. The null hypothesis was that the amount of sexual imagery in the experimental population would equal the amount of sexual imagery in the control population. And notice again that we only have two conditions. We have the experimental condition and we have the control condition. The next study that we looked at, Perceiving Facial Affective Ambiguity, a behavioral and neural comparison of adolescents and adults. It took a look at how well or how sensitive or how confused adults were versus adolescents when they were trying to judge the emotional expression on faces. And we had the null hypothesis that the zone of the category boundary for adolescents would equal the category boundary for adults. And again, notice that we're comparing two things. We're comparing the adults to the adolescents. And then finally, when we did the look at when more pain is preferred to less, adding a better end, and we took a look at that study where people would put their hands into ice water, and treatment number one, you had to hold it in there for 60 seconds. Treatment number two was the longer trial. You held it in there for 60 seconds, and then for an additional 30 seconds at a slightly warmer temperature to see which one people thought was less painful, which one would they prefer to go through again. And the null hypothesis is that whatever measure of pain you used, the average for the long trial in the population would equal the average for the short trial in the population. Once again, notice only two conditions, short trial versus long trial. That was the case for every single experiment that we looked at. Every single experiment only had two conditions, long trial versus short trial, experimental bridge versus control bridge, adolescents versus adults, chance responding versus ESP responding. It was only ever two conditions until we got to the chi-squared for goodness of fit. And the study on hockey success and birth rate, the relative age effect, that was the first time that we had more than one comparison to make. That was the first time we had more than two conditions. So we, in that study, took a look at players that were born in the early months compared to players that were born between April and June, to players that were born in July and September, and then finally from between October and November. And this was the first time that we had a null hypothesis where we wrote it out in English, but basically the null hypothesis was this. The null hypothesis was that the proportion of players in the NHL from born in January to March is going to equal the proportion born between April and June, is going to equal the proportion born between July and September, is going to equal the proportion born between October and December. That was expressed in an English sentence language, but that was the null hypothesis for the chi-squared goodness of it. And it was the first time that we had more than two conditions This time we had 4 conditions that the subjects could be categorized as. Now that was for categories, but let's say that we continued on with this research and we wanted to take a look at some quantitative variables. So let's say that we wanted to actually take a look at salaries of the players in the NHL. And do players who are born in the early months actually make more money than players that are born in the later months? So does that carry on even once you make it to the NHL? Do you still have that kind of skill difference as shown in the amount of money that they make if you're born early versus if you're born late? So if we were doing that study, the null hypothesis would be that the average salary for people born January to March, or for NHL players born January to March, equals the average salary in the population of players born April to June, equals the average salary for the population of players born July to September, equals the average salary for the players born October to December. So we have 4 different conditions. And you might say to yourself, well, we could possibly jerry-rig a t-test in order to take a look at those conditions, because even though we have 4 conditions, really your null hypothesis can be expressed as just a series of comparisons between 2 conditions. So you could take that equation right there that our null hypothesis has, and you could say, well, couldn't we just say our null hypothesis is that the average salary for players born January to March equals the average salary for players born April to June, and the average salary for January to March equals the average salary for July and September, and the average salary for January and March equals the average salary for October and December, and average salary for April to June equals average salary July to September, and average salary April to June equals average salary October to December. We got one more, and average salary July to September equals average salary October to December. Couldn't we just use the skills that we've already developed with the t-test and say, hey, we can analyze this question by just doing 6 t-tests and then seeing what pattern emerges, and we can make a decision based on those 6 t-tests. And this would be a possible solution except for one problem, and that problem is, there we go, that problem is the danger of multiple tests. And when you have multiple tests that you do in statistics, you have to be very, very careful to make sure that you are using techniques to get to the actual truth of the matter, and that you're not mistakenly lying to yourself and making errors and not really modeling what is going on in reality. So my favorite way of showing the danger of multiple tests is to give you a hypothetical situation to just kind of show you why you can't keep testing over and over and over and over again. So let's take a look at this situation here. Let's say that there are 2 friends and they're in high school, and one of the friends, she has a decision that she needs to make. She needs to decide whether or not she's going to break up with her boyfriend. And there are some reasons to stay together, and there are some reasons for her to break up. And she's really torn. She doesn't know what to do. So she decides, hey, you know what? I'm going to flip a coin. I'm going to flip a coin, and whatever comes up is what I'm going to do. So her friend is there. She tells her friend about it, and her friend is like, okay, let's do that. You clearly need to make a decision, but you're at a standstill. So let's use this test to help you make your decision. Okay, heads, you stay together. Tails, you break up. So they flip the coin. She flips the coin. It lands. Her friend takes a look at it and says, all right, tails, you break up. And the flipper says, wait, I wasn't ready. So they flip it again. It comes down again. Tails, you break up. And the flipper says, wait, the coin wasn't flipped high enough. So they flip it again. Tails, you break up. And the friend says, wait, the wind messed it up. So they flip it again. Tails, you break up. And the friend says, wait, it landed weird in my hand. So they flip it again. Tails, you break up. Wait, I flipped it too fast. So they flip it again. Tails, you break up. Wait, I flipped it too slow. So they flip it again. Heads, you stay together. And the friend says, I knew we were meant to be. So you can understand how this test was rendered meaningless because they just did it over and over and over and over again. They did it multiple times. And when you do a test multiple times, you lose the honesty of the test, you lose the truth of the test, you lose the test's ability to actually do what it was supposed to do. And you end up with situations like this where you can basically search until you find the answer that you're looking for. And this is a problem for sure. I mean, if you want to use coin flipping to decide your romantic involvements, then this is not the way to do it. But importantly, for statistics, we have to tie this in and understand the idea of the type 1 error. And what a type 1 error is. Your type 1 error is when you find an effect, when you find a significant effect, but in actuality, no significant effect exists. So the null hypothesis is the true hypothesis. It's the correct hypothesis. It's what's actually out there in reality, but you rejected the null hypothesis. You make a type 1 error. So that is basically the idea of a false positive. So you said that something is there. You say that an effect is real, when in reality, the effect is not real. You accept the research hypothesis or the alternative hypothesis, when in reality, the null hypothesis is true. That is called a type 1 error. And the probability that you're going to commit a type 1 error is equal to your alpha level. And typically your alpha level is 0.05. So what we as psychologists do is we say to ourselves, look, we have these statistical tests. And these statistical tests cannot tell us with absolute certainty whether or not a null hypothesis is rejected or accepted. But it can tell us how likely a null hypothesis, how likely a sample is based on the null hypothesis, right? So there's always that possibility that you get a sample that looks really, really weird, but it comes from a null hypothesis population. You just ended up with a weird sample. And the probability that you end up with a weird sample is your alpha level. And in most cases, the alpha level is going to be 0.05. And that is psychologists and researchers just being honest with themselves and saying, look, we're going to have to tolerate some risk. We're going to have to tolerate some risk of making a type 1 error and saying that an effect is there when the effect really isn't there. And we have collectively agreed that 5% is a good level of risk to have. And sometimes if you're doing medical research, they'll say we've collectively agreed that 1% is a good amount of risk, to take on. But the point is that you have to take on some risk. You always have some probability that you're going to make that false positive, you're going to make that type 1 error, and that is your alpha. And you want to make sure that whatever you do in your analysis, your alpha stays at the agreed upon level. In this case, your alpha stays at 0.05. And as we're going to see, when you do multiple tests, that does not happen. You start inflating your alpha, and your alpha can get out of control. So we're going to take a look at a study called The Analysis of Minnesota Multiphasic Personality Profiles of 40 College-Educated Overt Male Homosexuals. This was a study that was done back in 1964, and it reflects the scientific, cultural, and clinical biases of the time. It uses outdated assumptions. It uses an outdated, current at the time, but outdated now, personality test. But it is a cautionary tale about why multiple tests are an issue. So what did they do? Well, they recruited, the researchers recruited 40 homosexual men. These were all college educated, so they were all successful. They were all high functioning. And then they gave them the Minnesota Multiphasic Personality Inventory, which was the major personality inventory of the time. They recruited a comparison group of heterosexual men matched on age and education, and they broke the Minnesota Multiphasic Personality Inventory into its individual clinical scales, and then tested whether each of those clinical scales differed significantly between the homosexual males and the heterosexual males. So they took the 10 subscales and they ran a t-test on each of those subscales to test a null hypothesis of, does the mean responses of heterosexual males equal the mean responses of homosexual males? So just to kind of give you a breakdown of the table. So here we have the table. I'm going to populate it little piece by piece. So let's start putting stuff on there. So here is the scales that the Minnesota Multiphasic Personality Inventory has. We're going to take away the first 3 of those because those are just scales to indicate things like, are you lying on your test? So they're not actually the clinical scale, so we'll just get rid of those for a moment. And then just very briefly, I'll describe the 10 scales. So we have scale HS, which is hypochondriasis. So this assesses the pattern of physical concern and bodily focus, especially the degree to which a person tends to notice and worry about physical symptoms. Elevated scores may reflect chronic health anxiety, stress-related somatic complaints, or an attention to bodily sensations. A typical item might be, I seem to get sick more easily than most people. So that was that first scale. The next scale was depression, D. So the depression scale measures negative mood, reduced energy, withdrawal, pessimism, and social disengagement. Higher scores suggest sadness, low motivation, or feelings of hopelessness, whereas lower scores reflect emotional stability and positive engagement. A typical item is, I often feel that life is not worth the effort. The third one, hysteria, HY. The hysteria scale taps into stress avoidance, denial of emotional difficulty, and the expression of psychological distress through physical symptoms. People with elevated scores may manage stress by minimizing emotional problems, but experiencing tension physically. An item might be, I don't let things get me down even when they seem serious. Number 4, psychopathic deviate, PD scale. The psychopathic deviate scale measures nonconformity, independence, conflict with authority, and discomfort with rigid rules. It does not measure psychopathy in the modern sense. Elevated scores can reflect rebelliousness, dissatisfaction, or impulsivity, while lower scores indicate conventionality and rule following. A typical item might be, I often feel restricted by society's rules. Number 5, the masculinity-femininity scale. So the masculinity-femininity scale reflects traditional mid-20th century gender role interests. It mainly measured whether someone endorsed hobbies and preferences stereotypically associated with men or women at the time, liking sports, cooking, or reading certain magazines. A typical item might be, I enjoy mechanical or construction-related activities. So this is one of the ones that in the modern versions of this, it's considered outdated, culturally biased, not clinically meaningful, but it was there in this 1964 study. All right, number 6, paranoia. PA. The paranoia scale measures interpersonal sensitivity, suspicion, feelings of being criticized or misunderstood, and difficulty trusting others. Higher scores can reflect heightened alertness to threat or mistrust. Low scores suggest comfort with social evaluation. A typical item is, people often say things behind my back. Number 7, psychasthenia. PT. The psychasthenia scale assesses anxiety, worry, rumination, indecisiveness, and obsessive thinking. It closely resembles modern concepts of chronic anxiety or high neuroticism. Elevated scores indicate tension and overthinking. Lower scores indicate calmness and emotional regulation. A typical item might be, I can't stop worrying about things that might go wrong. All right, number 8, schizophrenia, SC. The schizophrenia scale captures unusual thoughts, social alienation, perceptual sensitivity, and difficulty organizing internal experiences. It does not diagnose schizophrenia. However, elevated scores may indicate unconventional thinking or distress, while lower scores reflect strong social connectedness. A typical item is, sometimes I feel disconnected from the world around me. Number 9, hypomania, MA. The hypomania scale measures energy level, impulsivity, excitement, and activity levels. High scores indicate restlessness, rapid thought, or stimulation seeking. Low scores indicate calmness and steadiness. A typical hypomania item might be, I often feel so energetic that I have trouble sitting still. And then finally, social introversion, the SI scale. The social introversion scale assesses introversion, social reserve, preference for solitude and discomfort in large groups. High scores reflect quietness and preference for small social circles. Low scores reflect sociability and ease in group settings. A typical social introversion item is, I prefer to spend most of my free time alone. All right, so those were the scales and what they measured. So as you can see, a wide variety of different personality and psychological dimensions. All right, those were the scores for the homosexual sample of 40 individuals. And then these were the scores for the sample of 40 heterosexual individuals. And then what they did was they did a t-test on each of those subscales. So they did a t-test for hypochondriasis. They did a t-test for hysteria. They did a t-test for psychopathic deviant. They did a t-test for all of those. And they ended up with these t-scores over here. And what we're going to do is we're just going to take a look at these piece by piece. I just need to move them over to the left there. And we're going to see why this was problematic. And the reason is that let's take a look at that first T statistic there, a 0.65 for the hypochondriasis scale. Now, the probability of making a type 1 error with one t-test, is 5%. That's your alpha level. That's what you've accepted. You can't get around that issue. So right now, we have a 5% chance after doing one test of saying that an effect is there, a difference is there between homosexual males and heterosexual males, even though the difference doesn't exist. All right, and that's just significance testing. That's just the game that we signed up for. That's just the risks that we take on. That's one of the reasons why replications are so important, but that's beyond our point today. The point is that when we do one test, we have already used that 5% chance of making a type 1 error. So what happens when we do our second test and we test the difference on the depression scale, it's like flipping a coin once and then flipping a coin again. And when you get heads, you get a false positive. So we flipped the coin once. Our coin is extremely unfair, right? We only have a 5% chance of getting heads. We only have a 5% chance of hitting that false positive. But the moment we do another test, we flip that coin again. And the probability of getting at least one type 1 error, the probability of getting at least one false positive goes from 5%, which we have decided is acceptable, it now goes to approximately 10%. So by doing two tests, you have almost doubled your chances of finding a false effect. You've almost doubled your chances of saying, hey, there's a difference between homosexuals and heterosexuals when there actually is no difference. And when you do that third test for hysteria, that alpha level now, that probability of making that type 1 error goes up to approximately 14%. And then when you do 4 tests, it goes to 19%. You do 5 tests, it goes to 23. 6 tests, it goes to 26. 7 tests, it goes to 30. 8 tests, it goes to 34. 9 tests, it goes to 37. And by the time you get that 10th t-test completed, you have a 40% chance, almost a coin flip now. You have a 40% chance of concluding that there is a significant difference when no significant difference exists. And the important thing to know is that we, as a scientific community, and these researchers, as scientific researchers, agree that they're willing to adopt a 5% risk, an alpha level of 5%, that they might make a type 1 error. But by using this procedure of multiple comparisons, they've actually accepted, unknown to themselves, they've accepted a 40% chance of saying that some difference is there when no difference actually exists. And that's just not good science. That's just not acceptable. That's the danger of multiple tests across multiple conditions. That Alpha level just explodes when you do more than the one test. So that was the issue that was with this test. That's a real world, happened in the world of psychology example of why you don't do multiple tests. And years later, when they did follow-up studies, when they took a look at reviews of all the literature that had been done on this question of the differences between homosexuals and heterosexual populations. So, for example, this review paper by Kunz Greitemeyer in 1982. So he did a review of the psychometric studies on homosexuality, studies like the Dean and Richardson study that we just took a look at. And he writes, the general conclusion is clear. These studies overwhelmingly suggest that homosexuality per se is not related to psychopathology or psychological adjustment. The few studies which suggest the contrary are among the weakest methodologically, and some of these are so flawed as to be uninterpretable. So weak methodology, weak statistics cannot be interpreted correctly, and yet out there in the world, out there published, influencing thoughts and opinions and policies, as we're going to see. So, however, the pattern of these differences is not sufficiently consistent to describe a typical homosexuality, personality, or adjustment style. To say that it's not sufficiently consistent means that the story changed when multiple tests were run. And if your story is changing when multiple tests are run, that means that you have detected a false effect because it's not happening over and over and over again. The effect is not real. It was just a false effect. It's supposed to only happen 5% of the time, but it happened way more because many of these studies used multiple tests. So these differences may reflect idiosyncrasies in the samples used, or they may reflect a general increased level of stress experienced by many homosexuals in a society that is generally intolerant of homosexuality. And that, again, is one of the real kind of downsides of this particular experiment, because this experiment was asking an important question, right? The homosexuality is a behavior. It deserves to be studied and understood just like any other behavior does. And if you take a look at the actual results that they reported, they did find some significant differences. So again, these significant differences are uninterpretable because they are the methodology and the statistics done was just poorly done. But for example, one of the ones that they found a significant difference in was SC and MA. No, not that one. Is it paranoia? No, they didn't find one in paranoia. Okay, I will back up. They didn't find one in paranoia, which you might expect. But some of these might be actual differences, which would help us understand, at least in 1964, the behaviors and the thoughts and experiences of homosexual males. The problem is that we cannot know which ones to interpret and which ones to ignore because the multiple tests were used, and that renders the entire analysis not something that is subject to ethical and rigorous interpretation. So multiple tests were used, effects were possibly found, or the probability of finding things that weren't there skyrocketed. And again, this was something that was published. A lot of research like this was published. And I'll just very quickly end with some of the implications of this research. So you had this research and other research like it being used as evidence in court cases that were being tried where homosexuals were denied immigration based on the idea that they had deviant personalities and deviant mental disorders. Their behaviors were these studies. I'm trying to talk around a little bit of some sensitive issues, but these studies were used to justify classifying certain homosexual behaviors as being deviant and immoral because they came from people who were judged as being deviant and immoral on their results of a personality questionnaire, deviant in terms of being different from heterosexual males. And then even after the APA removed homosexuality from the diagnostic and statistic manual, results like this result were still used to deny people employment, either as school teachers or in other walks of life. So it had a large impact. Studies like this had large impacts. And as that review mentioned, the effects of these studies that they found, the significant differences that they found, were most likely due to false positives, saying that something was there when something actually wasn't there, those type 1 errors, and those occurred because multiple tests were used, and the probability of a type 1 error went from 5% all the way up to 40%. So that is why it is not good enough to just say, well, let's just run some multiple t-tests and we'll just test condition versus condition until we have all the conditions tested. We need something that can test all the conditions at once. We need something that can do the idea of those multiple t-tests, but in one single test that preserves that alpha rate. And that is what we're going to get when we take a look at ANOVAs. So that is going to be it for today. Next time, we are going to continue our look at ANOVAs. We're going to start on SPSS for ANOVAs. We're going to spend a week on it because ANOVA is a big, complicated, it's not complicated, but it is multi-step. So we're going to spend a little bit of extra time on it, but that's all coming next week. And as for today, we are done.